Hello friends, welcome back to the course of fluid mechanics, and in the fifth quarter we are going to deal with buoyancy, metacenter, stability and rigid motion of fluid. Here in this course, in this quarter, we are going to establish expression for hydrostatic force on curved surface, which is a very important derivation from numerical solving aspect point of view. Then we are going to discuss buoyancy, buoyant force, center of buoyancy, Archimedes principle, stability of floating objects, fluids in rigid motion and fluids in rigid body rotation. Now let us begin our discussion with hydrostatic force on curved surface. Now here you can see in the diagram that we have curved surface which is carrying liquid. On right hand side we are not interested in the geometry, therefore this only section is relevant, and here we have horizontal projection of curved surface, and here on this line we have vertical projection of the curved surface, and this is caused by the curved surface AC, which is having some kind of regular or irregular shape. So here the forces involved are horizontal and vertical. We can talk them in terms of Fx and Fy, and the net force we have to find, that is resultant force, and the liquid weight is acting along vertical down direction, that we are referring as W. Now as I said, we have hydrostatic force resolved into two parts, horizontal and vertical. So horizontal is Fx and vertical is Fy plus weight. So here we have two relevant expressions which are governing the philosophy of calculating horizontal and vertical forces, in all to turn the resultant forces on the curved surfaces, and the resultant force is under root of kind of magnitude Fh square plus Fv square. That is the usual way of finding resultant of a force, and the angle involved, tan of alpha, is equal to the vertical component of force upon horizontal component of force. If you like, angle alpha, that is equal to tan inverse of Fv upon Fh. Now the hydrostatic force on curved surface, we have discussed these two equations, and when we have two different layers of fluids, say one is water having density rho W and another is oil having density rho O, so we have to find the resultant force for both, and that is to be considered for the breadth on which that is applicable. In case of curved surfaces, you have to find the resultant force accordingly. Mathematically, both the things we are doing in an autocratic way. So the resultant force is sum of all resultant lines, and every resultant line is vector sum of vertical and horizontal force, and that is equal to summation PCI AI, where PCI is pressure at the centroid of I fluid and AI is the area of the fluid. Therefore PCI we can rewrite as rho g HCI, where h is the height of the centroid for ith fluid. Buoyant force. A fluid exerts upward force on the body which is immersed fully or partially into it. The upward force has tendency to lift the body, therefore we call that force as buoyant force. Now here you can see that the downward force because of the weight is shown by longer arrow, as compared to the buoyant force, and the resultant effect will be that this solid will be submerged into. In case the buoyant force is more, the object will float, and when both are identical, the net force will be balanced. Now let us consider that a flat surface of thickness h and area A is submerged into the fluid. The submerging depth of the upper layer is, say, S. H is the thickness of the submerged surface, and here we have two forces as we have discussed. Rho G S A will be the force acting downwards, whereas the buoyant force acting upwards will be rho G S plus H into bracket multiplied by the area. The area is identical on either side. That makes the discussion safe. Thus, we have buoyant force as the force that fluid exerts in an upward direction on the body, which is partly or fully submerged. So F on the top surface, as we have seen in the earlier diagram, is rho G S A, and at the bottom it is rho G A into bracket S plus H. So the net buoyant force can be calculated as F bottom minus F top, and when you work that out, you are left with rho G H A, and H into A makes volume of the submerged object into the fluid. So rho GV is simply weight of the liquid whose volume is equal to volume of the plate. This is a very key point one must understand. Thus, here we conclude that the buoyant force is the weight of the fluid that is displaced by the plate. These are the technical terms we are developing here. Later on, get into our equations. So here I want to mention that the buoyant force is independent of the distance of the object from free surface. So here S is not involved into this equation. And moreover, the density of the object which is submerged is also not playing any role at this point. Moreover, the buoyant force does not depend upon the shape of the object. It is independent of the shape of the object. Center of buoyancy. A line of action of buoyant force on the object is called the center of buoyancy. Centroid of the displaced volume of the fluid is also referred as the center of buoyancy. Note that this is applicable for submerged as well as floating bodies. Archimedes principle. A Greek mathematician who was prevailing about 225 BC expressed the principle: a body is immersed in a fluid experiences vertical buoyant force which is equal to the weight of the fluid displaced by the body, and this buoyant force acts upward through the centroid of the displaced volume. Now here you can see that when rho is less than density of the fluid rho F, then the object is floating. Otherwise, when rho is equal to rho F, it is suspended, and when rho of the object is greater, the body sinks into the fluid. So here you can have explanation for why a stone is suspended into mercury but it is submerged into water. The buoyant force is summation of rho I G V I, and this is equal to weight W into displaced volume. So buoyant force is equal to floating weight minus body weight. stability in floating objects. So here you can see a curved surface and a ball into it. So this ball will be stable in this kind of geometry. Whereas on a flat surface also, when it is undisturbed, the ball is naturally stable. Whereas the ball will be totally unstable on such a curved object when the ball is on the top of the object. So when center of the body is not vertically aligned with the buoyancy center, what happens? Let us have a look at naturally stable object B. In this, we have buoyant force acting vertically upwards, whereas weight is acting vertically downwards, and the center of gravity and the buoyancy center, they are coinciding with each other. So this forms a naturally stable system like here. This is a wonderful analogy which is expressed in Sinjal Simbela book. Whereas we consider the object with higher weight at this edge, lower edge, so that the center of buoyancy and center of gravity, they are displaced away from each other. However, they are in a vertical line, and W is acting downwards, FB is acting upwards, and the heavier object which is at the lower portion makes the system stable, as in the case A for a curved surface and a ball. Whereas unstable situation like this kind of curved surface and a ball is prevailing in this diagram, where the heavy weight of the object is lying on the top. So W is acting downwards and FB is acting upwards. The center of buoyancy and centroid, they are displaced from each other, and this makes the system unstable, and this can overturn in this direction or in this direction. Let us have a look at this. So here the restoring moment, when comes into picture, will turtle the object in a particular direction and will try to attain the natural stability where the weight is downwards. This kind of not natural stability, this kind of astable where the weight is downwards. So here in case of ship, we have heavier objects at the center, down center, so that the system is stable. The metacenter height GM, G to M, is calculated as the distance between the center of gravity of the ship and its metacenter. The large metacentric height implies greater initial stability against overturning. Now we are in position to discuss fluids in rigid body motion. We have basic equation. The gradient of pressure is equal to rho into G bar. Here we have to understand in what direction G bar is acting. G bar is not a force, normally. We are considering having three components. We normally consider that G bar is acting downwards and it is in the negative direction of Z axis. So G bar, I am writing it is equal to minus G K cap, and therefore gradient of pressure is equal to minus rho G bar, where G bar is equal to minus G K cap. Now when the rigid body motion is considered for the fluid, we have fluid filled into a container, and that container is accelerated in some direction, which can be represented by A bar, which is external acceleration for rigid body motion. So the equation, hydrostatic equation, takes this form, and if we explicitly write del bar operator, that is gradient operator, we have I cap times partial derivative with respect to x plus j cap times partial derivative with respect to y plus k cap times partial derivative with respect to z operated on pressure plus rho plus rho g k cap, that is equal to minus rho into ax, that is x component of acceleration into unit vector along I direction, and so on for y component and z component of acceleration. Now acceleration in straight path we are going to consider, and for that we shall chart that there is no motion along y direction. So acceleration is appearing in x and z direction, and acceleration due to gravity is in z direction. That is k cap is involved in that. So this equation can be split into three independent equations as del p by del x is equal to minus rho ax, del p by del y is equal to 0 because there is no action taking along y direction, and del p by del z is equal to minus rho times g plus az. That is acceleration along z direction and acceleration due to gravity which is acting along z direction. Here this equation tells me that the pressure term is depending upon variable x, variable z, and it is independent of variable y. So P is function of x and z, and therefore exact differentiation for P can be written as del P by del x into dx plus del P by del z into dz. Here P is function of x and z. That's a point to remember. Therefore we can substitute del P by del x from our discussion here, minus rho ax, and del P by del z is equal to minus rho times into bracket g plus az. So this leads to expression dp is equal to so and so. Now we can integrate on both sides and we can find out that p2 minus p1, integration dp upper limit minus lower limit, is equal to minus rho ax into x2 minus x1 minus rho into g plus az times z2 minus z1. Now vertical rise in the free surface, if we consider smaller, p1 will be equal to p2, and our equation will be simplified, and the variation in the z coordinate of the surface dz will be minus ax times x2 minus x1 upon g plus az. So here you can have a look at the geometry, how the surface behaves, and when we are charting acceleration that is along x direction as well as z direction, the resultant will be in the plane xz. And if we like to see the constant pressure line, isobaric lines, these are the lines involved and this is the geometry involved. Now friends, we are in position to discuss rotation of fluid in cylindrical container. Let us suppose that this is a cylindrical container and this is rotated about z-axis, and unit vector along z-axis is indicated by k cap. This is the direction in which it is rotated. The angular velocity involved here is, say, omega bar, and the direction associated with omega bar is in the direction of z-axis, so can be denoted using k cap. Here the radius vector can be indicated using a unit vector I cap r, and the acceleration occurring is in this direction, whereas acceleration due to gravity is acting downwards. Therefore g bar minus a bar, this vector is acting in this particular direction, and in advance I want to notify you that this vector is normal to the constant pressure lines which are indicated here. Now in this discussion we are going to consider rotation about z-axis without translational motion, and as I said, omega bar is equal to omega k cap and r bar is equal to r times ir cap, and we are interested in finding acceleration, which is omega bar cross r bar, that is equal to minus r omega square ir cap. So this acceleration is occurring in the direction of unit vector IR cap with negative sign. So acceleration is occurring in this direction. Now our hydrostatic equation for accelerated motion, gradient of pressure is equal to rho times g bar minus a bar. The basic equation being gradient of pressure is equal to rho times g bar. Now we shall explicitly write del bar operator here, IR cap into del P by del R plus K cap into del P by del Z is gradient of pressure, that is equal to rho times now minus G K cap minus plus R omega square I cap. So here del P by del R, after comparing components associated with unit vector IR cap on left hand and right hand side, we can write equation del P by del R is equal to rho R omega square and del P by del Z is equal to minus rho G. Here I want to explicitly mention that G bar is directed downwards in our reference system. So magnitude of G is small g, which is 9.81 meter per second square, and this is directed vertically down, and the direction associated is minus k cap, whereas the direction associated with acceleration is IR cap. Now del P by del Z we were discussing, that is equal to minus rho into G, which we can write as minus gamma, and in advance I am writing that this derivative is derivative of some function with respect to Z, and that function I am indicating as f dash. Now separating variables, we are trying to solve these two differential equations, and we can solve this using the method of separation of variables. On left hand side we have dp, that is equal to rho r omega square into dr, and here this f dash we are writing as df by dz, and df is equal to minus gamma times dz. Now here, after integrating on both sides, we have integration dp is equal to p, and rho omega square is a constant quantity. Integration r dr will be r square upon 2 plus some constant of integration, and we consider that this constant of integration is independent of r, but it may be depending upon z, which is not involved in this expression. So f of z is kind of constant in this equation, and df, when we integrate, it is equal to f, and minus gamma times integration dz will be z plus c is the constant of integration. Now these equations we are again handling in a proper way. So the constant of integration f of z, we have f equal to minus gamma z plus c. So we can club these two equations together so that we have f replaced by minus gamma z plus c, and now our agenda is to estimate what is c. That can be estimated using boundary condition, and we shall consider that the pressure at the center, about the axis at the center, is P0, and the coordinates of that point we have rz equal to 0, 0, that becomes origin of the coordinate system, in which we are having one vector, one variable r and another variable z. So here when we substitute r equal to 0, this term will be 0, and when we substitute z equal to 0, this term is 0, and we have to replace p by p0, so our c is equal to p0, which represents pressure at origin. Now after substituting c as p0, we can rearrange the equation as p minus p0 equal to rho r square omega square upon z minus gamma z. So if we like to rearrange the equation in terms of z, we have p minus p0 upon gamma, which is rho g, plus r square omega square upon 2g, that is equal to, we can call some constant plus br square. So here we can interpret this equation as the pressure linearly depends upon z, whereas the pressure parabolically depends upon the radius. So linear and parabolic dependence can be understood from the power involved here, and we can look at the quantity P minus P0 upon rho g as some constant A and omega square upon 2g as constant B. Thank you.